So now let's go through some examples of interpreting some logistic regressions. Here we're looking at the Donner Party. We had a group of 87 people who traveled from Illinois to California in 1846 in covered wagons. Between exposure to extreme cold and famine, 39 of the 87 members had died when they were rescued. And then another one ended up dying shortly around that time as well. Conflicting sources as to whether or not 39 or 40, but a large portion of them had died from extreme famine and exposure to cold. And so here we've got a sample data set where we have 45 observations from this party. It includes the age, the gender, and the survival status for each of the members within our sample. One of the first things we want to do is look at our data. So if we do a cursory explore data analysis, we see that the distribution among the variables of status and gender and age by gender, we're able to see that it seems pretty clear that both age and gender have an effect on someone's survival status. But we need to figure out a way to come up with a model to take care of that. If we set died to 0 and survived to 1, this isn't something we can really transform our way out of. We need to do something a little bit more. And so one way we can think about the problem is we can treat survived and died as successes and failures arising from the binomial distribution, where the probability of a success is given by a transformation of a linear model of our predictors. So here would be a portion of the output that you would get from SPSS when you run the logistic regression analysis for using age as our only predictor variable in our logistic equation. We have the Wald or the chi-squared statistic in our table. That's going to be the square of your Z statistic. And looking at the variables in the equation portion of the output, we end up with our logit function being 1.819 minus 0.066 times the age. So you might start thinking, okay, how can I actually use this? What does this mean? So if I'm asked to determine the age, the probability of survival and the odds of survival for a newborn, I can take this formula and I plug in a 0 to solve for age. And then I get that the odds of survival are 6.17 with the probability of surviving being 86% chance. We can do the same thing if we're looking at a 25-year-old to calculate the odds of survival as well as the probability of survival. And, we can extrapolate it out to someone that's 50 years old. So you can take that model and just plug in the age to kind of figure that the odds and later the probability as well. If we look at the data, we see that we have very discrete responses. So we either have responses here at the bottom with 0 or others at the top that are 1. And that makes sense, right? Because it's a binary response. But when we graph the function of the logit, we end up with this S-shaped typed line. Because you're really kind of looking more at the probability that you're a yes versus a no when you're looking at the logistic prediction. And so if we're looking at our variables in the equation and we're looking at our logit function, we need to remember that an important property of the odds ratio is that they're always constant. It doesn't matter, what values the other independent variables take on. So here in this expression, you have our logit expression that we looked at. And with this, we can see that the effect of the odds of a 1 unit increase in age is going to be the exponent of that negative 0.066, which is the 0.936, excuse me, that 0.936 value in the upper right-hand corner of our variables in the equation graph chart. And so what this means is that the odds decrease by 0.936 minus 1 to get 6.4. So the odds decrease by 6.4%. So therefore, a unit increase in X is going to decrease your probability by 6.4%. So an increase in age decreases our odds by 6.4% regardless of what value of X we have. And to demonstrate this or illustrate this, we're going to look at a 1 increment increase in age decreasing our odds by 6.4 by looking at the logit function for X and the logit function for X plus 1. And so we're going to find the difference between the two logit function models, which ends up, once we work through it all, the exponent of that slope value that we saw before, and we end up with that value of 0.936 that we saw in the upper right-hand corner of that variables in the equation chart. And then once again, we subtracted 1 to get a negative 6.4%. So now we are going to look at, we said that earlier there definitely looked like something was going on between the different genders. So what if we put that in the model? What would that look like? And so once again, this is the variables in the equation portion of the output that we would get. But what's that mean, right? So now we, just like with our multiple linear regression models, we can take our values and plug it in directly. So here we can calculate what the value is when we are trying to predict the survival of a male model or male participant, or if we look at it for a female participant. And so we end up with two separate functions within our logistic regression context here. And so by using that as a dummy variable, we're essentially, remember, we're pulling these two models together to look at it within a multiple logistic regression output. And so when we look at all of the components of our SPS output, we can see that we don't have an ANOVA table that we're used to looking at, right? So typically you would look at the ANOVA table to figure out if the F-test was statistically significant or not, to look at that omnibus test or for the overall model. And that's just not here for our logistic regression. So how are we going to do our hypothesis testing? So instead of looking at all of the combinations together in the F-test, we're going to just have to look at each individual test by themselves. So if we look at this, we can see that neither one of our coefficients are statistically, oh no, I'm sorry, sex, gender, and age are both statistically significant at the 0.05 level. But let's look at testing for the slope of age. So the slope for the age is going to be beta minus 0 divided by our standard error. And we end up getting the z value of negative 2.10. So when we look at the area underneath the normal curve, that falls falls below negative 2.10 and above positive 2.10, we end up with the values of 0.018 for both sections. And so our total area under the curve for this would be 0.036. If we were to look at the confidence interval for the age slope coefficient, we can calculate that 95% confidence interval for both the logit and then later also the odds ratio. What I want you to notice is that the p-value for my z statistic is the same as the significance value, which we also have as a p-value for the Wald statistic in our SPSS output. Okay, let's look at another example where data collected from the Netherlands is looking at the ownership of pet birds and lung cancer. So here they identified 49 cases of lung cancer among patients who were registered with the general practice who were age 65 or younger and who had resided in that city since 1965. So with this, they also selected 98 controls from the population of residents having the same general age structure for having a total of 147 observations. So here, would be a little bit of the information of what the data set would look like. So we would have whether or not they had lung cancer, their gender, SS would be socioeconomic status. A lot of times you'll also see that as SES. BKs, if they had bird keeping, age, years of smoking, and then also average rate of smoking. And so you would have that for all 147 observations. And then here we would have a visual representation of that data so that we can kind of do a little bit of exploratory data analysis on it. And then, when we look at our output, we end up seeing that, if we kept all of our other predictors constant, then the odds of getting lung cancer for bird keepers versus non-bird keepers is going to be taking that estimate for bird keeper, exponentiating it to get 3.91. And if we're looking at the odds ratio for getting the lung cancer for an additional year of smoking, then we're going to go and we're going to look at the coefficient for years, because it would be our years smoking, exponentiate it to get 1.08. So once again, what do these numbers mean, right? So one of the most common mistakes that's made when we're working with logistic regression is forgetting how to treat our odds ratio and looking at the ratio as a probability. So one thing we need to keep in mind is that our bird keepers are not 4 times more likely to develop lung cancer than non-bird keepers. That's going to be the difference between relative risk and an odds ratio. So when I'm asking for the risk of the model, you're going to be looking at the probability that you have lung cancer given that you have birds divided by the probability that you have lung cancer divided by, or probability you have lung cancer given that you didn't have birds. And so when we look at this, to try and find the probability that you have lung cancer in a bird keeper, if we knew that the probability that they had lung cancer given that they didn't have birds was 0.05. So if we're going to use 0.05 as our lung cancer given no birds, so this section right here is, this section right here is 0.05. All here we plug in 0.05, right? And so that allows for us to end up with looking at the probability that we have lung cancer given that we have birds divided by 1 minus the probability we have lung cancer given birds divided by 1. Well, so if we already know this ratio, we know that that's 3.91. Okay, and so if we know that that's 3.91, we can algebraically rearrange the equation to figure out that if what the probability that we have lung cancer given that we have birds to be 0.171, and then we can take these two the value of the probability that we have cancer given that we have birds divided by the probability that we have lung cancer given that we don't have birds to get a relative risk value of 3.41. So that's really kind of where that comes from, and kind of how you can interpret that and how you can work through that.